Hello dear students, welcome to the lecture 9 of Software Engineering course. So today we are going to see software evolution. So the topics covered in today's lecture are
Evolution processes. Change processes for software systems. Program evolution dynamics. Understanding software evolution. Software maintenance. Making changes to operational software systems. Legacy system management. Making decisions about software change.
By the way, there is nothing random at these evolution processes in software engineering evolution, so don't get confused with biological evolution where everything is claimed to be random. By the way, I don't believe in randomness because there is nothing random in this universe. As being a software engineer, I think we know better that fact. Even our random number generators in our computers are not random at all. Okay, so let's return back to our topic.
Software change. Software change is inevitable. New requirements emerge when the software is used, the business environment changes, errors must be repaired, new computers and equipment is added to the system, the performance or reliability of the system may have to be improved. A key problem for all organizations is implementing and managing change to their existing software systems. Importance of evolution. Organizations have huge investments in their software systems, they are critical business assets. To maintain the value of these assets to the business, they must be changed and updated. The majority of the software budget in large companies is devoted to changing and evolving existing software rather than developing new software. A spiral model of development and evolution.
Okay, so let's check it. You see there is release 1. It is a start. It is starting from nothing, then we do specification, implementation, validation, operation, and release. Then same phases are passed again after the release. Why? Because you need to improve your software, update your software to keep it satisfying the requirements of the advancing technologies, advancing demands, and so this is the continuous progress.
Evolution and servicing.
So you see it can be illustrated as initial development. You have to have some initial development, of course. Then evolution, you see evolution continues itself because you continuously improve the software, you continuously give service to the client. Actually, a lot of money in today's modern programming is made from services. There are even softwares that is distributed free. However, the only services are paid, such as MySQL. MySQL is the free software. However, services are pay to have, and there is phase out.
Evolution and servicing.
Okay, so the evolution is described as
the stage in a software system's life cycle where it is in operational use and is evolving as new requirements are proposed and implemented in the system.
Okay, servicing is described as
at this stage, the software remains useful but the only changes made are those required to keep it operational, i.e. bug fixes and changes to reflect changes in the software's environment. No new functionality is added.
Okay, and there is phase out. These are the stages and these are descriptions of these stages of the software lifecycle.
The software may still be used, but no further changes are made to it.
For example, I think Windows XP. Windows XP can be still used, however, Microsoft does not give any, let's say, support to Windows XP. For example, let's look for it. Okay, it says here mainstream support ended on April 14, 2009 and extended support ended on April 8, 2014. So you see the support of the Windows XP has ended. However, they have some exceptions. Let's see their exceptions. End of support, timeline, reception. Anyway, I will just pass it.
Evolution processes. Software evolution processes depend on the type of software being maintained, the development processes used, the skills and experience of the people involved. Proposals for change are the driver for system evolution. Should be linked with components that are affected by the change, thus allowing the cost and impact of the change to be estimated. Change identification and evolution continues throughout the system lifetime. Change identification and evolution processes.
Okay, you see there is change identification process, then you make change proposals, then software evolution process happens, you develop improve the software, then a new system is published, and then it repeats the cycle with change identification process. Many of the software you use nowadays gets frequent updates, such as your bank mobile application or the games you play and such, until they phase out.
The software evolution process.
Okay, so let's check the process. You see, it starts with change request. Your clients demand something and you take them as change request, then you analyze the impact, then you do release planning, and release planning branches into fault repair, platform adoption, system enhancement. Then you implement the change and then check the release planning whether your change implementation is correctly done or you still miss something and such, and then system is released to the clients, then clients request something else, something new, and the whole cycle repeats until the software phase out. And change implementation, it is like proposed changes. It goes to the requirement analysis and it goes back and forth until you are satisfied with the requirement analysis. Then requirements are updated, then the software development happens and software evolves into a better one. Okay.
Change implementation. Iteration of the development process where the revisions to the system are designed, implemented and tested. A critical difference is that the first stage of change implementation may involve program understanding, especially if the original system developers are not responsible for the change implementation. During the program understanding phase, you have to understand how the program is structured, how it delivers functionality, and how the proposed change might affect the program. Urgent change requests. Urgent changes may have to be implemented without going through all stages of the software engineering process. If a serious system fault has to be repaired to allow normal operation to continue, if changes to the system's environment, e.g. an OS upgrade, have unexpected effects, if there are business changes that require a very rapid response, e.g. the release of a competing product. The emergency repair process.
Okay, change requests come when there is an emergency and you analyze the source code, modify the source code, and deliver modified system. So in an emergency mode, you have to fix the bug or exploit or the fault or whatever it is immediately. Therefore, it bypasses the software engineering usual stages, phases, and it gets patched to the software immediately. They are called as, I think, hot patches, if I remember. Hot patch. Oh, hotfix. Okay, hotfix, not hot patch, but hotfix. Okay. So let's get some idea related to hotfix.
A hotfix or quick fix engineering update (QFE update) is a single, cumulative package that includes information, often in the form of one or more files, that is used to address a problem in a software product, i.e., a software bug. Typically, hotfixes are made to address a specific customer situation. The term hotfix originally referred to software patches that were applied to hot systems, that is, systems which are live, currently running, and in production status rather than development status. For the developer, a hotfix implies that the change may have been made quickly and outside normal development and testing processes. This could increase the cost of the fix by requiring rapid development, overtime, or other urgent measures. For the user, the hotfix could be considered riskier or less likely to resolve the problem. This could cause an immediate loss of services, so depending on the severity of the bug, it may be desirable to delay a hotfix. The risk of applying the hotfix must be weighed against the risk of not applying it, because the problem to be fixed might be so critical that it could be considered more important than a potential loss of service, e.g., a major security breach.
Okay, so now you get more idea. You have more idea about this.
Agile methods and evolution. Agile methods are based on incremental development, so the transition from development to evolution is a seamless one. Evolution is simply a continuation of the development process based on frequent system releases. Automated regression testing is particularly valuable when changes are made to a system. Changes may be expressed as additional user stories.
Okay, handover problems. Okay, let's read about that.
Where the development team have used an agile approach but the evolution team is unfamiliar with agile methods and prefer a plan-based approach. The evolution team may expect detailed documentation to support evolution, and this is not produced in agile processes. Where a plan-based approach has been used for development but the evolution team prefer to use agile methods. The evolution team may have to start from scratch developing automated tests, and the code in the system may not have been refactored and simplified as is expected in agile development. Program evolution dynamics. Program evolution dynamics is the study of the processes of system change. After several major empirical studies, Lehman and Ph.D. proposed that there were a number of laws which applied to all systems as they evolved. There are sensible observations rather than laws. They are applicable to large systems developed by large organizations. It is not clear if these are applicable to other types of software system.
Okay.
Change is inevitable. The system requirements are likely to change while the system is being developed because the environment is changing. Therefore, a delivered system won't meet its requirements. Systems are tightly coupled with their environment. When a system is installed in an environment, it changes that environment and therefore changes the system requirements. Systems must be changed if they are to remain useful in an environment.
Okay, so let's see the Lehman's laws.
Lehman's laws.
Lehman's laws. Okay, so the law and the description. The law is continuing change, and the description.
A program that is used in a real-world environment must necessarily change, or else become progressively less useful in that environment.
Increasing complexity.
Increasing complexity. As an evolving program changes, its structure tends to become more complex. Extra resources must be devoted to preserving and simplifying the structure. Large program evolution. Program evolution is a self-regulating process. System attributes such as size, time between releases, and the number of reported errors is approximately invariant for each system release. Organizational stability. Over a program's lifetime, its rate of development is approximately constant and independent of the resources devoted to system development.
Okay, and we continue with the laws of the Lehman.
Conservation of familiarity. Over the lifetime of a system, the incremental change in each release is approximately constant. Continuing growth. The functionality offered by systems has to continually increase to maintain user satisfaction. Declining quality. The quality of systems will decline unless they are modified to reflect changes in their operational environment. Feedback system. Evolution processes incorporate multi-agent, multi-loop feedback systems, and you have to treat them as feedback systems to achieve significant product improvement. Applicability of Lehman's laws. Lehman's laws seem to be generally applicable to large, tailored systems developed by large organizations. Confirmed in early 2000s by work by Lehman on the Feast project. It is not clear how they should be modified for shrink-wrapped software products, systems that incorporate a significant number of COTS components, small organizations, medium-sized systems.
Okay. So the key points of the first part can be summarized as:
software development and evolution can be thought of as an integrated, iterative process that can be represented using a spiral model. For custom systems, the costs of software maintenance usually exceed the software development costs. The process of software evolution is driven by requests for changes and includes change impact analysis, release planning, and change implementation. Lehman's laws, such as the notion that change is continuous, describe a number of insights derived from long-term studies of system evolution.
Okay. So the part 2 of today's lecture.
Software maintenance. Modifying a program after it has been put into use. The term is mostly used for changing custom software. Generic software products are said to evolve to create new versions. Maintenance does not normally involve major changes to the system's architecture. Changes are implemented by modifying existing components and adding new components to the system.
Usually nowadays, if you deliver a custom software, you make more money, you generate more money from maintenance over the time. Okay. So if you be in a situation to outsource part of your software or a program or a software, you have to consider the cost of maintenance and updates and evolution and such. So it is not just I get the software and then it is done. No, it is not. Your software will have to maintain it, fix it, patch it, evolve and such. Okay.
Types of maintenance. Maintenance to repair software faults. Changing a system to correct deficiencies in the way meets its requirements. Maintenance to adapt software to a different operating environment. Changing a system so that it operates in a different environment, computer, OS, etc., from its initial implementation. Maintenance to add to or modify the system's functionality. Modifying the system to satisfy new requirements.
Okay, so this is a good pie chart for
Maintenance effort distribution.
you see functionality addition or modification takes 65% of your efforts. Environmental adaptation takes 18% of your efforts, and fault repair takes 17% of your efforts. Probably this is based on some statistical research and analysis. You have to look for the book to get its source.
Maintenance costs.
Okay, so this is the important part. Let's read it.
Usually greater than development costs 2 to 100 depending on the application.
Let's read it again.
Usually greater than development costs 2 to 100 depending on the application.
Okay, this means that the maintenance cost of the software may be 2 times greater than the software initial development, or it can be up to 100 times more costly than the initial development of the application. So you see how serious is the maintenance is. Okay.
Affected by both technical and non-technical factors. Increases as software is maintained. Maintenance corrupts the software structure, so makes further maintenance more difficult. Aging software can have high support costs, e.g. old languages, compilers, etc.
Okay, so there are some charts related to
Development and maintenance costs.
so you see system 1 takes about $220 for development and about 180 for maintenance, and the system 2 takes about $180 for development and $320 for maintenance. So it may be changed according to your system, software and such. So what are the cost factors in maintenance?
Maintenance cost factors. Team stability. Maintenance costs are reduced if the same staff are involved with them for some time.
Okay, so
Contractual responsibility. The developers of a system may have no contractual responsibility for maintenance, so there is no incentive to design for future change. Staff skills. Maintenance staff are often inexperienced and have limited domain knowledge. Program age and structure. As programs age, their structure is degraded and they become harder to understand and change.
okay, so these are the cost factors of maintenance. You have to consider all of them when you are going to rent a new software or when you develop a software for a client, and you are contracting for also maintenance as well, and they will ask you to give them a price range for maintenance costs, and you have to calculate that as well, of course.
Maintenance prediction. Maintenance prediction is concerned with assessing which parts of the system may cause problems and have high maintenance costs.
Okay, so when you are developing a system for a client, you have to also predict the maintenance cost, or you may be in a situation to predict the cost of future maintenance before you make the contract. So this is really important to determine the costs without that maintenance happens, or without you sign the contract.
Change acceptance depends on the maintainability of the components affected by the change. Implementing changes degrades the system and reduces its maintainability. Maintenance costs depend on the number of changes and costs of change depend on maintainability.
So,
Maintenance prediction.
okay, so when you are going to make a maintenance prediction, what parts of the system are most likely to be affected by change requests? First, you have to determine that how many change requests can be expected. Then you have to guess that, predict that. Then what parts of the system will be most expensive to maintain? You have to predict that, calculate that. What will be the lifetime maintenance cost of this system? This is crucial part when you are going to take a job from a client. And what will be the cost of maintaining this system over the next year? Because usually when you are doing a contract, the companies tells you that there will be 1 year maintenance for free, then the following years will be like 10% of the initial payment or such. So these aspects are extremely crucial, both when you are developing a system for a client and when you are purchasing a system from a developer or from a company. Okay.
Change prediction. Predicting the number of changes requires an understanding of the relationships between a system and its environment. Tightly coupled systems require changes whenever the environment is changed. Factors influencing this relationship are number and complexity of system interfaces, number of inherently volatile system requirements, the business processes where the system is used.
Okay, so you may be wondering what is a tightly coupled system. Let's look for that.
In computing and systems design, a loosely coupled system is one in which each of its components has, or makes use of, little or no knowledge of the definitions of other separate components. Subareas include the coupling of classes, interfaces, data, and services. Loose coupling is the opposite of tight coupling.
Okay, so let's look for tight coupling. I will look for that. Let's first check the
Advantages and disadvantages. Edit components in a loosely coupled system can be replaced with alternative implementations that provide the same services. Components in a loosely coupled system are less constrained to the same platform, language, operating system, or build environment. If systems are decoupled in time, it is difficult to also provide transactional integrity. Additional coordination protocols are required. Data replication across different systems provides loose coupling in availability, but creates issues in maintaining consistency. Data synchronization.
Okay, so you see this is the advantages and disadvantages. Okay, you may look for more information. Okay, there is also an article related to this. Okay, so let's read some more information related to that. Okay.
Loose coupling as a best practice. Decoupled or loosely coupled components are more independent and reusable, improving overall extensibility. Loose and tight coupling are quite general concepts. So, what use cases can benefit from each approach in practice? Before we discuss tight coupling, it should be noted that loose coupling is by far the most desired paradigm for RESTful API development. RESTful APIs should be able to transform, remix, scale, extend and morph from use case to use case across multiple resources. In essence, a proper REST implementation should be both layered and stateless. It should exist largely independently from a single use case, and should respond with all the information required to interface for all requests. Even outside of the requirements for authentic RESTful design, loose coupling is an excellent implementation for most modern use cases. Any API type should require minimal new work to leverage, allowing developers to use their knowledge across multiple implementations and interfaces. Fewer custom implementations mean a greater effort spent on building the core function, rather than building individual applications and interfaces for each new resource. Additionally, some significant security gains come with loosely coupling. Since there are not a million different versions of a million different interfaces for each resource, the amount of data that needs to be secured and updated could be reduced dramatically. Loose coupling, in effect, leads to a much more secure ecosystem. Finally, smart and dumb components are largely isolated from one another, reducing overfetching. In other words, smart components that require more knowledge or data to function can do so by talking to a centralized API. Dumb components that don't need to know much can operate independently without contending with coupled, unique resources or requirements. Ultimately, loose coupling leads to decreased interdependency between components and reduces the risk of breaking changes.
Okay, so what about tight coupling as an alternative?
Tight coupling as an alternative. If loose coupling has so many benefits, why even consider tight coupling? While it's true that tight coupling is not optimal for most microservices and RESTful designs, it does have a place in specific applications. The primary benefit of loose coupling is that resources are decoupled from the interface to allow for greater amounts of interoperable, extensible APIs and resource schemas. Not all services require this, however. There are some cases where one has a single resource and a single interface of a single type. In such a case, singular purpose APIs are often tied to single use cases and single workflows. Loose coupling also introduces greater complexity to a system. Some workflows only utilize one device, one interface, and one API. If only a single implementation is planned, tight coupling could make for a much simpler development effort. Unless there's a strong possibility that the application will move to something more general, simplicity is far preferred.
Okay, so there is an example. Let's see. This is tight coupling. There is public class remote, private television TV, protected remote, static remote, static remote control. Okay. So this is the type coupling. And I think this is the loosely coupling. You see they have different interfaces and classes for each class. Okay, so this is the loose coupling. Okay, let's continue.
Complexity metrics. Predictions of maintainability can be made by assessing the complexity of system components. Studies have shown that most maintenance effort is spent on a relatively small number of system components. Complexity depends on complexity of control structures, complexity of data structures, object, method, procedure, and module size. Process metrics may be used to assess maintainability, number of requests for corrective maintenance, average time required for impact analysis, average time taken to implement a change request, number of outstanding change requests. If any or all of these is increasing, this may indicate a decline in maintainability.
Okay.
System re-engineering. Restructuring or rewriting part or all of a legacy system without changing its functionality. Applicable where some but not all subsystems of a larger system require frequent maintenance. Re-engineering involves adding effort to make them easier to maintain. The system may be restructured and redocumented.
Okay.
Advantages of re-engineering. Reduced risk. There is a high risk in new software development. There may be development problems, staffing problems, and specification problems. Reduced cost. The cost of re-engineering is often significantly less than the costs of developing new software. The re-engineering process.
Okay, so the re-engineering is a more preferred method because there is always risk of updating your entire system, entire software. Because as time passes, you find the bugs, exploits, and fix them. However, when you deploy a new software, there can be lots of new bugs, new exploits, and such. So it reduces the risk. There is a good saying: if a system is working, let it be, don't update it. It is of course not true at every case. However, if you won't get a substantial benefit from deploying a new system, you may choose to continue with re-engineering. Okay. So the re-engineering process is like here: original program, source code translation, reverse engineering, program structure improvement, and program documentation, program modularization, restructured program, and re-engineered program, data re-engineering, original data, and re-engineered data.
Re-engineering process activities.
Okay, so the code, source code translation is converting code to a new language. This can be done, of course. You just recode the existing classes, methods, and whatever there are into a new programming language. We can say that, for example, from C++, you may move to C Sharp. Okay. Or from Java, you may move to Python and such. Okay. Reverse engineering, this is a really complex and hard area. Analyze the program to understand it. And program structure improvement, restructure automatically for understandability. Program modularization,
Program modularization.
okay, modularization. Reorganize the program structure, and data re-engineering, clean up and restructure system data. Okay.
Re-engineering approaches.
So there are two main, I think, let's see each of them. Automated program restructuring is an approach. Program and data restructuring is an approach. Automated source code conversion is an approach. Automated restructuring with manual changes is an approach. Restructuring plus architectural changes is an approach. You see, from left to right, the cost increases. If you use automated source code conversion, it is the cheapest one. If you use automated program restructuring, it is a cheaper one. If you use automated restructuring with manual changes, it is somewhat middle at the cost. And if you use program and data restructuring, it is pretty expensive. And if you use restructuring plus architectural changes, it is the most expensive approach.
Re-engineering cost factors. The quality of the software to be re-engineered. The tool support available for re-engineering. The extent of the data conversion which is required. The availability of expert staff for re-engineering. This can be a problem with old systems based on technology that is no longer widely used.
Okay, so you see, if you re-engineer a pretty old software, you may have hard time to find engineers experienced in that technology, and if you even find them, they would be pretty experienced, pretty senior, and therefore their cost would be much higher. Okay.
Preventative maintenance by refactoring.
Okay, this is also really important aspect of program maintenance.
Refactoring is the process of making improvements to a program to slow down degradation through change. You can think of refactoring as preventative maintenance that reduces the problems of future change. Refactoring involves modifying a program to improve its structure, reduce its complexity, or make it easier to understand. When you refactor a program, you should not add functionality but rather concentrate on program improvement.
Okay, so let's find an example. Okay, I will try to find a better article because this is important. Okay. Okay, let's read this article. This looks like a good one, I think.
7 Code refactoring techniques in software engineering. Being a developer, how do you start working on a new project? Firstly, you gather some basic requirements, and then based on the requirement, you start implementing the feature one by one. As you progress with your project and learn more about it, you keep adding and changing the code in your codebase. Later, you also change the code to fix the bug and edge cases. But what happens after a couple of days or months? How your code looks like, is it complicated? Is it hard to understand? If yes, then definitely you didn't pay attention to improve your code or to restructure your code. You might have written some duplicate code without looking at the existing code, or you may have written some longer methods, functions, large classes, too many parameters, non-intuitive variable names, code placement, etc. Improving or updating the code without changing the software's functionality or external behavior of the application is known as code refactoring. It reduces the technical cost and makes the code more efficient and maintainable. If you don't pay attention to the code refactoring process earlier, you will pay for errors in your code later. So don't ignore cleaning up the code.
Okay, I think there is a point I want to get to your attention again. I always see this as a problem. Non-intuitive variable names. Variable names are really important because if someone else or you, even you, read it again at a later time, you would have a lot of time, a lot of hard time to understand, to remember what was it, or in case of someone else, they would have a lot of hard time to understand what does that parameter, what does that variable means. Okay, so intuitive variable names are really important, and as a whole, code refactoring is also really important. Let's continue.
In a software development process, different developers have different code writing styles. They make changes, maintain the code, extend the code, and most of the time they leave the code without continuous refactoring. Unrefactored code tends to code rot, a lot of confusion and clutter in code such as duplicate code, unhealthy dependencies between classes or packages, bad allocation of class responsibilities, too many responsibilities per method or class, etc. To avoid all these issues, continuous refactoring is important. Now the question is, what are the techniques to refactor the code? We will discuss some popular and common techniques to refactor the code, but before that let's discuss some quick tips. Tips: you need to perform code refactoring in small steps. Make tiny changes in your program. Each of the small changes makes your code slightly better and leaves the application in a working state. Run the test TDD and see after making small changes in the refactoring process. Without running these tests, you create a risk of introducing bugs. Do not create any new features or functionality during the refactoring process. You should refactor the code before adding any updates or new features in your existing code. Refactoring process can affect the testing outcomes, so it's good to get your QA and testing team involved in the refactoring process. You need to accept that you won't be fully satisfied with your code. Your refactored code will be outdated in near future and you'll have to refactor it again.
Okay, so these were the tips. So let's see.
Most common code refactoring techniques. There are many approaches and techniques to refactor the code. Let's discuss some popular ones. Red-green refactoring. Red-green is the most popular and widely used code refactoring technique in the agile software development process. This technique follows the test-first approach to design and implementation. This lays the foundation for all forms of refactoring. Developers take initiative for the refactoring into the test-driven development cycle, and it is performed into the 3 district steps.
Okay, so write just enough code to pass the test. So first you write the test, and you write the code to pass the test. Then refactor, optimize, clean up without adding new functionality and with confidence. So you write enough code to pass the test. After you pass the test, you refactor it, and if your refactor fails the test, write a code again to pass the test and refactor it. Okay.
Red. The first step starts with writing the failing red test. You stop and check what needs to be developed. Green. In the second step, you write the simplest enough code and get the development pass green testing. Refactor. In the final and third steps, you focus on improving and enhancing your code, keeping your test green.
So it starts with a red circle. You write a test, and of course your software will fail it because you didn't update your software for passing that new requirement, new test. And then you write the code to pass the test, and then you refactor it and check again whether it is passing or it is failing. Okay.
So basically, this technique has 2 distinct parts. The first part involves writing code that adds a new function to your system, and the second part is all about refactoring the code that does this function. Keep in mind that you're not supposed to do both at the same time during the workflow. Refactoring by abstraction. This technique is mostly used by developers when there is a need to do a large amount of refactoring. Mainly we use this technique to reduce the redundancy, duplication, in our code. This involves class inheritances, hierarchy, creating new classes and interfaces, extraction, replacing inheritance with the delegation, and vice versa.
I have shown abstract classes in object-oriented programming, so you may watch that programming lecture videos. They are also on our YouTube channel. So there are client code, abstraction layer, and cloud supplier. Then client code abstraction layer, new supplier. So abstraction layer keep your code in an order, okay, because your new reading code has to be satisfy the rules of the abstract classes, abstraction rules, abstraction layer, okay. So let's read further.
Pull-up push-down method is the best example of this approach. Pull-up method, it pulls code parts into a superclass and helps in the elimination of code duplication. Push-down method, it takes the code part from a superclass and moves it down into the subclasses. Pull up the constructor body, extract subclass, extract superclass, collapse hierarchy, form template method, extract interface, replace inheritance with the delegation, replace delegation with inheritance, push down field. All these are the other examples. Basically, in this technique, we build the abstraction layer for those parts of the system that needs to be refactored and the counterpart that is eventually going to replace it. Two common examples are given below. Encapsulated field, we force the code to access the field with getter and setter methods. Generalize type, we create more general types to allow code sharing, replace type checking code with the state, replace conditional with polymorphism, etc.
Okay, and the third methodology is composing method.
During the development phase of an application, a lot of times we write long methods in our program. These long methods make your code extremely hard to understand and hard to change. The composing method is mostly used in these cases. In this approach, we use streamline methods to reduce duplication in our code. Some examples are extract method, extract a variable, inline temp, replace temp with query, inline method, split temporary variable, remove assignments to parameters, etc. Extraction, we break the code into smaller chunks to find and extract fragmentation. After that, we create separate methods for these chunks, and then it is replaced with a call to this new method. Extraction involves class, interface, and local variables. Inline, this approach removes the number of unnecessary methods in our program. We find all calls to the methods, and then we replace all of them with the content of the method. After that, we delete the method from our program.
Okay, so another approach is
4. Simplifying methods. There are two techniques involved in this approach, let's discuss both of them. Simplifying conditional expressions. Refactoring, conditional statement in programming becomes more logical and complicated over time. You need to simplify the logic in your code to understand the whole program. There are so many ways to refactor the code and simplify the logic. Some of them are consolidate conditional expression and duplicate conditional fragments, decompose conditional, replace conditional with polymorphism, remove control flag, replace nested conditional with guard clauses, etc. Simplifying method calls. Refactoring, in this approach, we make method calls simpler and easier to understand. We work on the interaction between classes, and we simplify the interfaces for them. Examples are adding, removing, and introducing new parameters, replacing the parameter with the explicit method and method call, parameterize method, making a separate query from modifier, preserve the whole object, remove setting method, etc.
okay. Let's read the rest as well.
Moving features between objects. In this technique, we create new classes, and we move the functionality safely between old and new classes. We hide the implementation details from public access. Now the question is, when to move the functionality between classes or how to identify that it's time to move the features between classes. When you find that a class has so many responsibilities and too much thing is going on, or when you find that a class is unnecessary and doing nothing in an application, you can move the code from this class to another class and delete it altogether. Examples are, move a field, extract class, move method, inline class, hide delegate, introduce a foreign method, remove middleman, introduce local extension, etc.
Okay.
Six. Preparatory refactoring. This approach is best to use when you notice the need for refactoring while adding some new features in an application. So basically it's a part of a software update with a separate refactoring process. You save yourself with future technical debt if you notice that the code needs to be updated during the earlier phases of feature development. The end user cannot see such efforts of the engineering team eye to eye, but the developers working on the application will find the value of refactoring the code when they are building the application. They can save their time, money, and other resources if they just spend some time updating the code earlier. It's like I want to go 100 miles east, but instead of just traipsing through the woods, I'm going to drive 20 miles north to the highway, and then I'm going to go 100 miles east at 3 times the speed I could have if I just went straight there. When people are pushing you to just go straight there, sometimes you need to say, wait, I need to check the map and find the quickest route. The preparatory refactoring does that for me. Jessica Kerr, software developer.
Okay. So you see, you start programming, and before going to destination, you do preparatory refactoring. Okay.
7. User interface refactoring. You can make simple changes in UI and refactor the code. For example, align entry field, apply font, reword in active voice, indicate the format, apply common button size, and increase color contrast, etc. Final words. You need to consider the code refactoring process as cleaning up the orderly house. Unnecessary clutter in a home can create a chaotic and stressful environment. The same goes for written code. A clean and well-organized code is always easy to change, easy to understand, and easy to maintain. You won't be facing difficulty later if you pay attention to the code refactoring process earlier. Two of the most influential software developers, Martin Fowler and Kent Beck, have devoted their time to explain the code refactoring process and the techniques of it. They have also written a complete book on this subject, Refactoring, Improving the Design of Existing Code. This book describes various refactoring techniques with a clear explanation of working on these refactoring process. We recommend you to read this book if you want to go in depth with the code refactoring process.
Okay. So now you get the idea of refactoring and why it is so important. Okay.
Refactoring and Re-Engineering. Re-engineering takes place after a system has been maintained for some time and maintenance costs are increasing. You use automated tools to process and re-engineer a legacy system to create a new system that is more maintainable. Refactoring is a continuous process of improvement throughout the development and evolution process. It is intended to avoid the structure and code degradation that increases the costs and difficulties of maintaining a system.
Okay, so
Bad smells in program code. Duplicate code. The same or very similar code may be included at different places in a program. This can be removed and implemented as a single method or function that is called as required. Long methods. If a method is too long, it should be redesigned as a number of shorter methods. Switch case statements. These often involve duplication, where the switch depends on the type of a value. The switch statements may be scattered around a program. In object-oriented languages, you can often use polymorphism to achieve the same thing.
Okay, so this duplicate code is a very big no-no. You should never have any duplicate code because it really degrades your overall code cleanness. And if you want to make a change in future, you have to find the code everywhere where you have used it and change all of them. However, if you use only a single code, your change will be reflected in everywhere that your code is being called, executed. So the second part of
Bad smells in program code. Data clumping. Data clumps occur when the same group of data items, fields in classes, parameters in methods, reoccur in several places in a program. These can often be replaced with an object that encapsulates all of the data. Speculative generality. This occurs when developers include generality in a program in case it is required in the future. This can often simply be removed.
okay.
Legacy system management. Organizations that rely on legacy systems must choose a strategy for evolving these systems. Scrap the system completely and modify business processes so that it is no longer required. Continue maintaining the system. Transform the system by re-engineering to improve its maintainability. Replace the system with a new system. The strategy chosen should depend on the system quality and its business value.
Okay. Okay, figure 9.13, an example of a legacy system assessment. So there is business value and system quality. When system quality increases, there are things that increases also business value. So low business value with low quality is of course at the low end. So if you have high business value but low quality, you get only the quality of business value. If you have high business value and high quality, you get better of both, and low business value and high quality. So this is the example of a legacy system assessment. This is how you assign an importance to a legacy system. So let's say you have a legacy system and you consider redesigning it, okay, and however you want to evaluate its let's say value. Therefore, if your business have high value and high quality, you get the 0.678, and if you have high business value, if you have high business value and low quality, you get 9 and 10. So this actually tells you that either you should re-engineer your legacy system or not. If you get 9 or 10, you should re-engineer your legacy system. I think we can say that.
Legacy system categories. Low quality, low business value. These systems should be scrapped. Low quality, high business value. These make an important business contribution but are expensive to maintain. Should be re-engineered or replaced if a suitable system is available. High quality, low business value. Replace with COTS, scrap completely or maintain. High quality, high business value. Continue in operation using normal system maintenance.
Okay, so here they are explained. If you have low quality and low business value, just scrap the software. If you have low quality but high business value, you should re-engineer or replace your system to have high quality and continue with your high business. If you have high quality but low business value, You should replace with cut, which was commercial off the shelf. That means get a ready generic software and replace it, or scrap completely it or maintain it. And if you have high quality and high business value, you can continue in operation using normal system maintenance.
Business value assessment. Assessment should take different viewpoints into account: system end users, business customers, line managers, IT managers, senior managers. Interview different stakeholders and collate results.
Okay, and
Issues in business value assessment. The use of the system. If systems are only used occasionally or by a small number of people, they may have a low business value. The business processes that are supported a system may have a low business value if it forces the use of inefficient business processes. System dependability. If a system is not dependable and the problems directly affect business customers, the system has a low business value. The system outputs. If the business depends on system outputs, then the system has a high business value.
okay, with this way you may assess, evaluate your business, and there is system quality assessment.
System quality assessment. Business process assessment. How well does the business process support the current goals of the business? Environment assessment. How effective is the system's environment and how expensive is it to maintain? Application assessment. What is the quality of the application software system?
Okay, and
Business process assessment. Use a viewpoint-oriented approach and seek answers from system stakeholders. Is there a defined process model and is it followed? Do different parts of the organization use different processes for the same function? How has the process been adapted? What are the relationships with other business processes and are these necessary? Is the process effectively supported by the legacy application software? Example, a travel ordering system may have a low business value because of the widespread use of web-based ordering.
okay. So let's see factors used in environment assessment.
Factors used in environment assessment. Supplier stability. Is the supplier still in existence? Is the supplier financially stable and likely to continue in existence? If the supplier is no longer in business, does someone else maintain the systems? Failure rate. Does the hardware have a high rate of reported failures? Does the support software crash and force system restarts? Age. How old is the hardware and software? The older the hardware and support software, the more obsolete it will be. It may still function correctly, but there could be significant economic and business benefits to moving to a more modern system. Performance. Is the performance of the system adequate? Do performance problems have a significant effect on system users? Support requirements. What local support is required by the hardware and software? If there are high costs associated with this support, it may be worth considering system replacement. Maintenance costs. What are the costs of hardware maintenance and support software licenses? Older hardware may have higher maintenance costs than modern systems. Support software may have high annual licensing costs. Interoperability. Are there problems interfacing the system to other systems? Can compilers, for example, be used with current versions of the operating system? Is hardware emulation required? Understandability. How difficult is it to understand the source code of the current system? How complex are the control structures that are used? Do variables have meaningful names that reflect their function?
You see, meaningful names is really important both for you and other people that reads your source code.
Documentation. What system documentation is available? Is the documentation complete, consistent, and current? Data. Is there an explicit data model for the system? To what extent is data duplicated across files? Is the data used by the system up to date and consistent? Performance. Is the performance of the application adequate? Do performance problems have a significant effect on system users? Programming language. Are modern compilers available for the programming language used to develop the system? Is the programming language still used for new system development? Configuration management. Are all versions of all parts of the system managed by a configuration management system? Is there an explicit description of the versions of components that are used in the current system?
So if there are explicit description of the versions, it is better. Okay.
Test data. Does test data for the system exist? Is there a record of regression tests carried out when new features have been added to the system?
If there are test data, it is better. I think these are very clear requirements or evaluation techniques.
Personnel skills. Are there people available who have the skills to maintain the application? Are there people available who have experience with the system?
So let's recap. Factors used it in environment assessment: supplier stability, failure rate, age, performance, and factors used in environment assessment. Okay, we continue. Support requirements, maintenance costs, interoperability, factors used in application assessment, understandability, documentation, data, performance, factors used in application assessment, programming language, configuration management, test data, personal skills. And let's continue.
System measurement. You may collect quantitative data to make an assessment of the quality of the application system, the number of system change requests, the number of different user interfaces used by the system, the volume of data used by the system.
Okay, so let's see the key points of this second part.
Key points. There are three types of software maintenance, namely bug fixing, modifying software to work in a new environment, and implementing new or changed requirements. Software re-engineering is concerned with restructuring and redocumenting software to make it easier to understand and change. Refactoring, making program changes that preserve functionality, is a form of preventative maintenance. The business value of a legacy system and the quality of the application should be assessed to help decide if a system should be replaced, transformed, or maintained.
Okay, let's read the key points again because they are really important and really well summarize the part 2.
There are three types of software maintenance, namely bug fixing, modifying software to work in a new environment, and implementing new or changed requirements. Software re-engineering is concerned with restructuring and redocumenting software to make it easier to understand and change. Refactoring, making program changes that preserve functionality, is a form of preventative maintenance. The business value of a legacy system and the quality of the application should be assessed to help decide if a system should be replaced, transformed, or maintained.
Okay, so it is enough for today. We are going to make an addition to your project requirements. I mean your final project. So let's open the project description file here, and I will copy it from another project description. It is actually not an extra work for you, not an extra requirement, but it will make my evaluation of your lecture attendance better. Okay. So, what is it? Everyone will be sending a Word or PDF document along with their final project files. This document will contain screenshots of your all comments to the lecture videos, all of the 14 lecture videos. If there be more, of course you will be also have to make more. Take screenshots with high resolution so that I can read your comment with easiness and clearly. Those who fail to send this document will be counted as not attended to the lectures. Therefore, they will get effect. So basically, you will just capture the screenshots of your comments, put them into a file, a Word file or a PDF file, and send me that. So I will be able to see all of your comments with easiness. So I will be able to tell that, oh, this student has commented lecture 3 this and lecture 4 this and lecture 5 this, and so I will be able to evaluate your lecture attendance with much easiness. Okay, so let's upload today's lecture slides to our GitHub repository. I think I have forgotten something here. Let's update the last update date of the project file, project description file, to be more precise. Okay, so please try to avoid from coronavirus. It's a serious disease. Stay safe. Hopefully see you next week. End of lecture.